we're working on vectors. We had a kind of introduction yesterday. This is essentially going to be an introduction to three-dimensional vectors. God, my brain has gone. Did we touch anything on the vectors? Did we do anything particular, or are we really just way at the start? Or did we do anything even? Can anyone remember?
We discussed the beginning of vectors in 3D.
But nothing.
Well, you got to the vectors with I, J, and K.
Ah, good. Right. Yep, kicks in. My brain's working. Right, let's get you some definitions out of the way then. There are two kinds of things that you're going to see occasionally mentioned. One of the groups, are people getting kicked out all the time or just not staying? Because that's me just got another bunch of people who never made it. Right, a scalar in this section means a single number. Example, 14 is a scalar. Now, certain variables are scalar. If I said to you, your age, that would be a scalar, right? It's a number. If I said your weight, it would be a scalar. If I went and said to you the cost of a theatre ticket, that would be an example of a scalar, right? So it's a number. Whereas we say it only has magnitude, which means it only has a size. And then you have a vector. Well, a vector has magnitude, it has a size, and it has a direction. So in a very general sense, without going into what dimension we're talking about, some vectors are big and some vectors are small. They have magnitude, right? They have size. There is something weird going on with Zoom. That's two more people just came in. I got a feeling people are getting kicked in or kicked out all the time here. Right, so magnitude, and we have direction. For instance, these two vectors are the same magnitude, essentially the same length, right? But would you agree that they have different directions? So what kind of things can be thought of as vectors? Well, how about wind? You know, wind is blowing. Doesn't the wind have a direction? It's blowing northeast, and it's blowing northeast at 30 mile an hour or 10 mile an hour, right? So as a magnitude, that would be an example. So if you ever see the word scalar or vector, this is the kind of thing they're talking about. A scalar is a single number. It's a thing that only has size, magnitude. Whereas a vector has two properties. It has a magnitude and it has a direction. Oh, and when you do vectors, can't we do them like 1, 2, 4? And we can do them as 1i, 2j, plus 4k, right? They're examples of some vectors, right? That's what they might look like. Now, I want you to imagine, because I'm really bad at drawing, that this is a rectangle in three-dimensional space. Can you imagine it's kind of pointing out the way? And I'm going to call this guy A, B, C, D, and that guy right in the middle, I'm going to call him E. If I have a vector B, C, I'm talking about that guy, right? And if I have a vector C, D, I'm talking about the vector from C to D, right? There's a start and a finish. Let's talk about visually, right, geometrically, what adding two vectors is like. If I did this vector and I added this one to it, what vector would it be the same as? What single vector would adding these two combine to?
BD.
Does that make sense? That when you combine two vectors, what you're really doing is combining two journeys, right? Two direction magnitude combinations. I like the word journey in these stories. So you travel from here to here and then from here to here. But the overall journey is really just starting at B and finishing at D. Here's a different question. There's a vector BC, which is this guy. Is there any other vector in this diagram which is the same as the vector BC?
AD.
Would you agree? That these two guys are the same. Now, how do you compare two vectors to decide they are the same? They have to be the same length, right, magnitude, and they have to be pointing in the same direction. Now, here's another thing. These two are very similar, but they are not equal to each other. And the difference is the direction that you travel. A to D, you go this way. D to A, you go that way. In the vector world, you would say that AD is the same as the negative of DA, or if you wanted to, I guess you can phrase it the other way around. And what that tells us, say if you want to take a vector and you just want to do one thing, nothing else, just one thing, change its direction, don't you just stick a negative in front of it? So imagine I had a vector 1, 2, -1. And I'll call this vector U. If I wanted another vector which was exactly the same as this vector, but pointing in the other direction, and I'm going to call that vector V, wouldn't it be -1, -2, +1? Does that make sense? That if you want to do one thing only, and that is change the direction that you travel along that line segment, right, the vector, all you need to do is change its components from plus to minus and vice versa. So in the algebra world, isn't U the negative of V? Or V is the negative of U? It's a bit, depends which way you want to say it. Are we okay with this? This is very general, right? We're not, for the most part, getting too specific. Because this is true for two-dimensional vectors. It's true for three-dimensional vectors, which are the ones we're going to focus. But theoretically, at least, isn't it also true about 11-dimensional vectors? Even if I can't imagine what they look like, I can still imagine what the negative of it would be, right? It'd be the same vector, but going the other direction. So here's basically our 3D stuff now. Here's a very straightforward question. I have 2 points, and I'm not going to make any attempt to pretend that I'm drawing them right, but can you imagine P is here and Q is there? And I want to find the vector joining P to Q. So essentially, how far in the X direction, then the Y direction, and then finally in the Z direction do you need to go to start at P and end up at Q? And I like this notation. So I'm using the like the two brackets that look like greater than or less than, but they're not. And I'm going to call this guy x1, y1, and z1. And I'm going to call this guy x2, y2, z2, which is, I hope, the way I labeled them when we did the distance formula. What formula do you think you would use to find a vector joining P to Q, involving all these x1s and y1s and x2s and z2s? Any ideas?
Would you just go like x2 minus x1, y2 minus y1, z2 minus z1?
Almost right, but z2 take away z1. Apart from that, you nailed
I was about to say z, but I didn't know.
it. Does that make sense? It's basically destination take away start, right? Destination. And that's actually how I do it in my head. When I'm doing the vector between 2 points, I just say second takeaway first, second takeaway first, second takeaway first. So in this question then, it's going to be 2 takeaway 1, 1 takeaway 4, and -4 takeaway -2. So if you just say second takeaway 1, that's probably a little bit easier. Of course, that vector will become 1, -3, -4i2, -2, which is fine. What will the vector QP be equal to? And I don't need to do any real work. I should be able to just tell what the answer is going to be.
-1, 3, and 2.
Now, if you did it from scratch, wouldn't you have to relabel these? Wouldn't you basically say Q goes here and P goes here? And if you did the calculation, can you trust me? That's exactly what you get. Let's check it out. 1 takeaway 2, 4 takeaway 1, -2 takeaway that. You see it works. Have I convinced you that PQ and QP are the negatives of each other? So far, so good? Let's do a silly one. The vector P to P. Actually, the vector P to P, wouldn't it be a dot in 3D space? And using the formula here, since this guy is the same as that guy, because P is your start and P is your finished, won't you get 0, 0, 0? And that's a very interesting vector. It's very often written as 0 with an arrow above it. In textbooks, because they can do it in textbooks, it's a bold, because all vectors are bold, and it has a name. I hope I haven't mentioned the name because I've kind of given away the plot here. What name would you give this vector if you were the guy in charge of naming this vector? And you had no imagination.
0 vector.
And guess what? It is called the 0 vector. Now, that's a 3-dimensional 0 vector. Can you get a 20-dimensional 0 vector? There's no reason that couldn't happen. 0 vectors are quite interesting. We don't go into it because we don't do that much with the calculations in vectors. But very often, when you'd want to do balance of forces, right, where you get various forces pulling at a point and you want them to be balanced, right? So basically everything cancels everything out. What you're trying to do there is you're trying to solve a vector equation that's equal to 0, 0 vector, essentially. And if something is balanced, right, all the forces are 0, the object, whatever it is, stays put. And in construction and bridges and things like that, I think they're probably looking for balanced forces Because can you imagine if you had a big, tall girder? You don't want the forces to be pulling it over to the side, really. That wouldn't be a very good thing to do in the long run. Imagine I've got a vector. I'm going to call the first one U and the second one V because I have no imagination either. 1, 4, -3, and 2, 5, 1. And I was asked to do what is sometimes called the algebra of vectors. Now, the algebra of vectors is essentially how do you combine vectors, add, subtract, things like that. Well, let's look at adding. Oops, sorry. Yeah. I'll write that again. Suppose I wanted to add these two vectors together. And you've never done a physics class in your life, so this is brand new to you. What would be the most obvious method that would be intuitive to add two vectors?
Adding the X, Y, and Z's together.
Yeah. Add the X components together, add the Y components together, add the Z components together. In which case, this one, I believe you get 3, 9, -2. Isn't that nice when math makes sense? That there isn't a weird thing that you have to do when you add vectors, right? It's not. Well, that's how you add. And I'm going to show you what that looks geometrically, but let's get the algebra out of the way first. Let's look at subtracting. Suppose I had a vector u and I wanted to subtract the vector v from it. Would you agree that you're going to take this guy and subtract that guy? So it'd be u take away v. So 1 take away 2, 4 take away 5, -3 take away 1, and I got a -1, a -1, and a -4. So far, so good. Now, going to introduce the word scalar that I talked about today. And we're going to look at scalar multiples. And that is, you take a vector and you multiply it by a number like 2 or 3. So, first time you've seen a vector in your life, what would be a sensible way of calculating what 3 u's would look like?
Multiply the X, Y, and Z's by 3.
So 3 times 1, 3 times 4, 3 times -3. Aren't vectors doing what vectors should do? They are being sensible. Right? You add them the way you would expect to add them, you subtract them, and you multiply them by things like 2. What about 4u plus 2v? Well, isn't that really a combination of scalar multiples and some adds? Would that make sense? So 4u plus 2v would be 4 of this vector added to 2 of that vector. Right, 4 of this vector is 4, 16, -12, added to 2 of this vector, which is 4, 10, and 2. And when you add these vectors together, 4 add 4 gets you 8, 16 add 10 gets you 26, and -12 add 2, I believe, gets you -10. So can't you get any scalar combination of two vectors, right? 3 times one vector, add or subtract 5 times the other vector. Couldn't I also expand that whole process up to 3 vectors? Couldn't I do u plus v plus w? Couldn't I do 2u plus 3w minus 5v in any other combination I want as well? Are we comfortable with the algebra of vectors is pretty much intuitively obvious, right? What you would have thought you do, that's exactly what you do, right? Which is nice. Now, wind back a little bit. I'm not going to make attempts to make these accurate because it's 3D and it wouldn't look right even if I tried. So these are like visualizations. Can you imagine that this is what U looks like? And this guy down here, make him a little bit more obviously longer. Make this guy here V. Can you imagine that's a visual representation of these two? Now, what would a visual representation of adding these vectors look like? Well, you would take the vector U and you finish there. And where you finish, you pick this guy up and you stick him down here. And the vector U plus V would be the red vector. Geometrically, does that make sense what you're doing when you're adding two vectors? You're like adding two journeys together and saying what a single journey would look like from the beginning to the end. If you've done some physics, I believe they have a name for this. They call it the triangle of forces. You heard that term? So when you add two vectors, you can essentially create a triangle. Now, I've been a bit over generous with my spacing, so I'm going to have to squeeze the next one in. Let's look at what that guy would look like. Well, you start off with U, and you end here. Now, if I was doing V, wouldn't I be going down this way? Just like I did there. But this fella here can be thought of as adding the negative of V, right? So what you will do is you will go this way. And that's what negative V looks like. And now you join the start to the finish. And this is what U take away V looks like. Does that, I don't know how good I am at drawing, but does that kind of get you the gist of what's happening? Now, the next ones I can do much easier. What does a scalar multiple look like? Well, if that's U, can you imagine? Maybe a little bit more. There, that's what 3U looks like. It's like one of them, two of them, three of them, right? It's just a vector 3 times as long, but pointing in the exact same direction, right? They're parallel. So can you visualize what add, subtract, and scalar multiples of vectors now look like? Here's a little, I don't know if it's a trick question, but I have a vector U, I have a vector V, I have a vector W, I'm running short of letters, so U, V, W, X, Y. I don't want to use X, Y, and Z, so I have a vector K. And I have U plus V plus W plus K. What does that add up to based on the picture that you can see here?
Zero.
The journey started here, but didn't it also finish here? So won't the net effect be to start at a point and finish at the same point? Isn't that essentially what a zero vector is? You don't go anywhere. Are we okay with that basic? Right. So now let's return to, I'll do another U and V. I've done those, enough of these. Let's do 1, -1, 2. V is going to be 3, 0, -4. And W is going to be -2, -1, 1. Right, so they're the three vectors I'm going to deal with. We have already done add, subtract, and linear scalar combinations, so I'm not going to do any of them. I am going to do this fella, however. What are you being asked to do when they write that down? This is from yesterday. What is this guy?
Is it the distance?
It is. What we would call, in the language of vectors, we would call this the magnitude of the vector u, which is how long it is, right? Now, how do you get the length, the magnitude, of a single vector? We showed you how to get the length yesterday. Remember P, Q, all that carry on? But there isn't a P and a Q. There is just a vector. And I'm going to call this vector u x1, y1, and z1 so we can have a formula to work with. Don't make your life hard. What do you think the formula for the magnitude of a vector with components x1, y1, and z1 would be? It's the square root of something. What's the something?
X squared plus y squared plus z squared.
And I'm glad you got the letter right. Isn't that nice that it's really just the distance formula? Well, you might say, where's the other number? But if you really need another number, couldn't you just do the origin 0, 0, 0? Think of it like that if you want. Now, in this case, then, it's the square root of 1 squared plus -1 squared plus 2 squared, 1 plus 1 plus 4, square root of 6. So in this particular case, that's as good as it can get. But sometimes you have to make the, the radical look pretty. Well, let's up the ante. Actually, let's up it a lot. 2u take away v plus 3w. What we're going to find now is the magnitude of this fella. Well, I really have to do some work here, right? Finding the magnitude is going to be the last thing, right? The square root bit is going to be the last thing I'm going to do. Shouldn't I find what this vector is first? And then once I know what this vector is, then I can find its magnitude. Well, I'm going to cut some corners here because I hope that it's not too difficult. If you take two of these guys, you get 2, -2, and 4. Take away this guy, 3, 0, -4, and add 3 of these guys. Oh, God, I hope I can get it. -6, -3, 3. Just about made it. Now, you want to do this, you can then say 2, take away 3, add -6, -2, take away 0, add -3, and 4, take away -4, add a 3, and let's see what that gets me. 2 take away 3 is -1, then another 6, yikes, -7. -2 take away nothing is still -2, Then you add a -3, so this one's -5. And then 4, take away -4 is add it, so that's 8. 8 add 3 is 11. I wish I'd thought this thing through before I made the question up. Now I can get the magnitude. It's the square root of -7 squared, -5 squared, plus 11 squared. That's 49, 25, and 121. Oh, not as bad as I thought. It's the square root of 195. Quick scan in my brain. It might simplify. I'm not 100% sure it can. It definitely won't work with any of the evens, so it might work with 9. No, it doesn't. Could work with 5, but 5's not a perfect square, so I'll try 25. I'm just going to say, as far as I know, that's as good as that one gets. I can't find any simplification. You might have found one that I missed, but it looks good. Have we any questions about the algebra? These are examples of me doing it.
On WebAssign, would
yeah.
you have to simplify that? Or can
I
you leave
would,
it?
even if WebAssign is happy with it, I would just do it for good math reasons. Right? I'm sure that if you did simplify it, WebAssign would definitely accept that answer because it's the best answer. It might not. I can't see an answer to make that better, but somebody might come across and say, hey, well, I know who it doesn't work with. It doesn't work with any of the even numbers, right? So I don't need to do 4s and 16s. What would the next one be? 64.
Factors are 5, 3, and 13. So
Okay, so that's not going to work. Yeah. So we cool with that? Because I want to move on to some more new stuff still in vectors. Okay. Let's look at an idea called the unit vector. With the exception of the 0 vector, every vector can be converted into a unit vector. A unit vector is a vector the same direction but whose magnitude is 1. So if you want a unit vector of some vector v, then a unit vector is a vector, we'll call it u, that's the same direction as v, but whose magnitude is 1. So here's an example of what that question might look like. Find the unit vector of this vector. Call it u. So I have to figure out a strategy for finding a vector that's traveling in the same direction as this one. So can you imagine that this is what v looks like? But I want a little vector u whose length is 1, right? Any ideas for what I should do first to get closer to that?
To find the magnitude.
Okay, so let's find the magnitude of v. It's 3 squared, -4 squared, 12 squared. It's 9, it's 16, it's 144. I believe, check on this, is it 169? I'm assuming it is, right? Oh, that's a good one, isn't it? Don't expect nice answers, but this time we got one. So how do I find the unit vector? Well, the unit vector of V is 1 over the magnitude of V, the vector V. In other words, just multiply the vector V by this fraction. In our case, the fraction is 1/13. And a scalar multiple gets me that guy. Since this vector, right, this vector u is a scalar multiple of this, doesn't it mean it's going in the same direction? Right, if you multiply a vector by 2, it's still the same direction, it's just 2 times bigger. And if you multiply it by a half, isn't it the same direction, but half the size? Well, in this case, I'm making it 1/13 the size. Well, won't that make it 1 unit long? And you can check it. Do you know the magnitude of this vector is 1? Okay, let's try that again. Suppose I wanted to find the unit vector for 2, 2, 1. The magnitude of this vector is 4, add 1, square root of 9 is 3. So the unit vector is 1/3 of V. And that is 2/3, 2/3, 1/3. That look okay? How to find a unit vector. Right, make it horrible now. Okay, Kathy, give me a number 1 to 10.
6.
Okay, James, give me a negative number 1 to 5.
-4.
Okay, Ian, give me a positive number 1 to 3.
2.
I just wanted the numbers to be different. Right. So don't expect this one to be pretty, but I want to show you what an ugly one looks like, because you have to deal with whatever you're given, and you don't always get nice round numbers, right? So this is going to have its magnitude of these guys. And I hope that you lot haven't given me a nice answer. Yay, good, you haven't. It's the square root of 56. Which I can simplify a little bit, can't we? I'm saying, can't we? I'm about to find out if I'm right. Yes, you can. Anybody know what 56 can become?
2 root 14.
Yeah. So it's going to be 4 14s. So it's 2 root 14. Okay. So now we can get the unit vector. Time, that'd be quick. The unit vector is 1 over, right, this guy, right, that length, and the vector V, which is this guy. Now, if I bring these inside, so this is just the mechanics of ugly answers, right? That is, technically speaking, correct, isn't it? It is a unit vector. It's the same direction as V, and I guarantee that its length is 1, so that makes it a unit vector. However, I don't think that's anywhere near what we need for style points. Right, should look better than that. I'm going to do it in 2 stages. Cancel this guy, 3 over root 14. Cancel this guy, -2 over root 14, and cancel this guy, oops, comma, 1 over root 14. You all happy about the cancelling? That wasn't a major issue. What do you think I'm going to do next? Because I don't like square roots in the bottom.
Rationalize.
Yeah. So this is going to be 3 root 14 over 14, negative 2 root 14, 14 over 14, and root 14 over 14, which is nice. And also only 99% right. Is there anything left to make it pretty?
Your middle term. That's a 7, not a 14.
Ooh, did you all catch that deliberate mistake? Now, I do not know where from here to here WebAssign is going to say, you got it. I could do variations on a theme. Would you agree that this and this is the same vector? Here's another variation on a theme. Would you agree that this is also the same vector? Pulling out
The
a common
middle
fact.
term and the 1 over
I
14 should be negative.
Oh,
Don't
it
like
should be
that.
2.
Yep.
Okay. Fixed it. You agree with me now? Right. Well, there's about 5 or 6 flavors of the right answer there. Now, WebAssign might be really generous and take all of them. That would be really nice. I would love it to only take that one, because that one is really, in my opinion, the best answer. It's a single vector, simplified as much as possible, rationalized denominator as well. These two guys are quite closely related. I don't like them because you're now writing your answer as a multiple of a vector, but that's me being nitpicky. I don't like this one anyway because of the root 14. Don't like this one at all because I haven't even simplified. And this one here, the middle term has obviously got an issue. So when you do find the unit vector questions, you may want to play about with the version of your answer. If WebAssign says, no, don't like it, maybe they wanted, hopefully, they wanted a rationalized denominator. Hopefully, because that's what you should do. I think almost finished. I want to do one last quick thing in the last few minutes we've got. Right, take you through a 5-minute tour of your homework in 12.2. What do you think a theatre ticket is? A vector or a scalar? The cost of a theatre ticket.
Scalar.
It's a scalar. And it's a scalar because it only has magnitude, right? So that's how you're going to answer those questions. AB, which is A to B, is equal to one of these 4 guys. A to B is equal to that one.
See.
And that's those ones. We've covered that. There's some more of the same kind of thing, but this time journeys. Won't A to B plus B to C be A to C? Now, if you click on this, you want to write down that funny little arrow. So somewhere over here, there's a heading saying vectors. If I click on that, right, do you see the box that has an arrow on it? I can now type in, what's that going to be? A to C. Right. So if you're wondering how do you do that, that's how you do it. Now, in later questions, you're going to do vectors, right? You do not type this in, or at least I don't think it will like it. Oh, darn it again. I got to bring my keyboard nearer to me. Right. You see this funny little bracket here? If you look really carefully, can you see that the bracket has a slightly different look to it? If you type this in, WebAssign will say you're wrong. So just remember to hit that vector thing to keep it there. Because you know there are going to be questions like 2i plus 3j. Remember the ij notation? You do not type in, it wouldn't make sense in this question, but don't type in 3i plus 4j. Well, certainly don't do it with capitals. What you need to type in is, I've lost the darn things, vectors. 3i plus 4j. Now, if you look, you see how they're bold, right? And I have seen these issues before, and it's so easy to, you just forget it, right? Oh, the answer's funny little bracket 3, 4, 5, and why is it saying it's wrong? It's not wrong, you just haven't given it the right brackets, right? So vectors use this bracket, or they use ijk, and if it's letters, typically you're using that. Find the distance between two vectors, right? We've done that. And they've got a funny little picture here, but it's not as bad as it looks. Isn't the vector A to B? Well, here's the 4 pictures. If I shrink it down, you might be able to see them. There's only one of these pictures that is right. Do you know which one it is? If this is A to B, right? Won't the vector A be the same length, same direction? So pick that one. Does it allow me to pick it? Yeah. What's wrong with this one? Well, same length, wrong direction. This is B being joined to A, which is not what you were asked to do. This one is A being joined to B, and who knows what that is, but it isn't the same thing. So there's only one that fits all the bill. Here's the same kind of question again. Here are 2 vectors and being added together, and they've been kind of nice about it, but when you look at the pictures, only one of these pictures represent it. You recognize the triangular forces. Here's the algebra. Oh, have you noticed that they use the ijk notation? Me personally, I don't like it because I'm careless. If I have little funny brackets, it's easier for me to keep track. But it does mean that when you type in the answer, I would hope, don't quote me in this, you'll find out the first time you do it. I hope you could just simply put in the answer 1, 2, 3 and it'd be happy. But if it's not happy with that, won't you have to do 1i plus 2j plus 3k, if that's what it was, right? I hope it allows both notations, because if it is, me personally, I would do all my answers using that notation because I make fewer mistakes when I do that. And do you recognize linear combinations and magnitudes? We've covered that. Another bunch of questions, same idea. Another bunch of questions, same idea. Here is a vector, find the unit vector. Here is a vector, find the unit vector. Oh, I forgot about this one. So let's talk it through. I want a vector the same direction as this one, but whose length is 6. We know 3/4 of how to get that answer. We've already done it. So here's how you should do it. Take this vector and find its unit vector. And then multiply it by 6. So it's still it's a unit vector question with a little times 6. If you wanted it to be 4 times, wouldn't you just unit vector times 4? Okay, this question here is the same, and I have kept you enough, and oh, would you believe it, exactly on time. So I'm actually glad I scanned that because I missed the last question. So say hi, everybody, and have a nice weekend. I shall see you Monday, and I will hang about for anybody who has some homework questions.
Have a good one.
You too. Bye-bye, guys.
Thank you.
You're welcome.
I don't have a question.
Anybody got a question? Well, that happens. That's a good sign, right? It means whatever you're doing right now, you're coping quite well with it, and you're not having any great issues. Vectors are pretty easy, in my opinion. Do you think so far there've been
Wait,
nothing
David.
to?
Did David have a question?
Yeah, actually, I did.
Oh, sorry, David. Yes, what you got? I ignored you there, David. Sorry.
So when we were doing the distance for like the more complicated 3 vectors, where we did like 3u plus 2v or whatever, can you combine it all into one step instead of splitting it off, doing it into 2 steps like you did? Like in the parentheses of the distance formula, could you just add the x's in the one bracket for the x, then plus the y's all in one go?
The answer to that might be yes. Let me tell you what I think you're saying. And if you're saying it, then I agree with you. It doesn't mean you're saying it badly. It just means I'm getting old and I don't understand things. Right. Let's suppose you had a vector u. I'm going to make the numbers easy because the numbers aren't the important thing. This guy is 1, 1, 1. And this guy is 1, 0, 1, right? Keep them nice, easy numbers, right? And suppose your question was to find the magnitude of this fella, right? What I'm hearing you say is that you do this calculation in your head, put the x guy and square it, put the y guy and square it, and put the z guy and square it, and just basically do it in all one big go. Is that what you're saying, David?
Yeah, so like in the parentheses for the x's, for example, you could just put 1 plus 2 times 1 minus
take away 1. Yeah, and so that would be 3 take away 1, so 2 would go there. And then the next one would be 1 of these, add 2 of these is 4, take away nothing, it's still 4. And then it'd be 1 of these, add 2 of these is 5, take away 1 of them is 4. Yes.
Okay.
I make too many mistakes to do that. I have learned, it's a good idea to know your weaknesses. And I'm aware of them. I don't always pay attention to them, but I'm aware of them. And that is definitely okay. I suggest homework. I have not a problem with that. Test questions, please do everything the long way. Not because it helps you get the question done faster, because it doesn't. But if you screw up, can't I at least see where it went wonky? And I can give partial credit. If you cut out too much of the middleman, let's just say, for argument's sake, you forgot about the takeaway W. Wouldn't these 3 numbers be virtually random numbers then? It'd be hard for me to, I can't go through and say, well, I wonder if he added it instead of subtracted it. I wonder if he forgot the middle, all the permutations it could have. That's not, I can't do that. I can't say, I know Sam, he's just careless. He just forgot the last guy. If I don't see it, I can't give you it. So homework, go for it. Test, show me everything, right?
So what I was asking was, is it okay if I do show you everything just inside the parentheses? So I go inside the parentheses for the first one, I put 1 plus 2, then in parentheses another 1 for the Vx, then minus.
Oh, so
1.
your answer would look something like this: 1 plus 2 plus 1 squared. 2 plus 2 plus nothing. I should be saying takeaway, shouldn't I?
Yeah.
Takeaway squared. Yeah, that's better. That's essentially you showing me the working. So I would be able to tell from there what you were doing to get those numbers. So you'd be okay there. I was assuming that you were doing even less work than that, which you might do. I can imagine once you've done enough of these, couldn't you probably do a lot of it in your head in the same kind of way I did this?
Yeah.
And that's okay. You know, I don't want you to do busy work. You know, if you can do some, you know, fast, do it. You'll know the great thing about web design is it says you're wrong. So, you know, if you didn't do it, you can say, oh, okay, I better be a little bit slower with this second shot.
Yeah.
Any other questions?
That was my only question.
Okay, well, I think that's us finished for this week.